Hey guys, so in this video we're going to start talking about torque acceleration problems, also known as rotational dynamics problems, where we have two types of motions. What that means is that on top of having a rotation, we're also going to have objects moving in a linear direction. So it's going to have a combination of both of them. Let's check it out. So remember that when we have problems where a torque causes an angular acceleration, alpha, we use the rotational version of Newton's second law. So instead of F equals ma, we're going to write torque, sum of all torques equals I alpha. Okay? So then when we have torque alpha questions, that's how we solve it. But in some problems, we're going to have more than just alpha. We're going to have rotational and linear motion. So for example, here in this picture, if you have a block that's connected to a pulley, if you release the block, it's going to accelerate this way, but because it's connected to the pulley, it's also going to cause the pulley to accelerate this way. So the block falls in linear motion and the pulley accelerates around its central axis in rotational motion. We have both. And in these questions, we're not going to use just torque equals I alpha, but instead we're going to use both torque equals I alpha and F equals ma. Okay, so we're going to write sum of all forces equals ma for each acceleration we have, and we're going to write sum of all torques equals I alpha for each alpha that we have. So for each a, we write F equals ma, and for each alpha, we write torque equals I alpha. Now, what do I mean by each a and each alpha? You have to count how many motions exist in the problem. Here I have one object with one acceleration, one type of motion, linear motion, and then here I have another object with another type of motion. So there's two motions in total, okay? But if you had more types of motions, and I'll get to that in the example below, you would use more than just two equations, all right? We'll get to that. When you do this, when you combine F equals ma with torque equals I alpha, you end up with an A and an alpha. That's two variables. One of the techniques we're going to use to solve these questions is instead of having A and alpha, we're going to replace alpha with A. And by doing this, instead of having A and alpha, I'm going to have A and A. Imagine in this second equation here, imagine if that alpha somehow became an A, then you would have A there and A here. And that's good because instead of having two variables, you now have one variable. This is a key part in solving this question is going from alpha to A, okay? And the way we do this is by remembering that A and alpha are connected. They're connected by this equation. A equals R alpha, where R is the distance between the force and the axis of rotation. So it's our R vector from the torque equation, if you remember. So where R is distance, I'm going to call this distance to axis, okay? Distance to the axis from the force, okay? But this is actually not the equation we're going to use because what we're looking for is we're trying to replace alpha. So what we're going to do is we're going to say alpha equals A over R. Wherever we see an alpha, we're going to replace it with an A over R, and that's going to simplify, okay? So we're actually going to use in these questions a combination of three equations. F equals ma, torque equals I alpha, and we're going to use this one here to link the two first equations. All right? The last point that I want to make here is that the signs for A and alpha, as well as the signs for V and omega, must be consistent. Must be consistent. What do I mean by that? So I'm going to give you one example that allows me to talk about these four variables. And it's this one. You have a disk that's rolling. Actually, let me draw it. You have a disk that rolls up a hill. Okay? So imagine that if you are going this way, right? And then you're going this way. Okay? Let me draw it over here. You're spinning like this. And then you go up the hill spinning like this. So that's your V, and this is your omega, okay? But if you're going up a hill, gravity is pulling you down, So your acceleration is downhill. It's going to be like this. And this means your alpha is actually like this, okay? Because if your velocity, if you're going up like this, means that your omega is like this, then an acceleration that's down means that your alpha is like this, all right? And all of these signs have to be consistent. So in most of these problems, because these are dynamics problems, they're problems about acceleration, we're going to say that the direction of positive will follow acceleration, okay? So let me add that here. Direction of, I meant to make a little star, direction of positive will follow acceleration. So this will be positive, right? Which means V is negative. And if V is negative, omega has to be negative as well, because V and omega must have signs that are consistent with each other. And alpha must be positive, okay? So A and alpha are positive together. In this particular situation, V is opposite to A, so it's negative, and omega goes with V. So omega goes with V, and the sign of A goes with alpha, okay? It's very important those signs are consistent. All right, let's do an example here. Before we solve an actual full-length problem, what I want to do is show you some of the things that I've talked about here in a variety of different examples. Let's check it out. So here, for each one of these, we want to solve for acceleration. First thing I want to know is which equations would you start with? How many equations, what kinds of equations, all right? So, and then we're going to sketch a diagram. So remember what I told you, remember what I told you that you write this point right here. We write F equals ma for each A, and we write torque equals alpha for each alpha. So what that means is that you look at this system here. Let's say that this mass is bigger than this, so that the system tilts this way, right? This means you have an acceleration here, and this thing is going to accelerate up, and this thing is going to accelerate this way. These are linear accelerations. The pulleys are also going to accelerate in this direction. Notice that all the accelerations are consistent with each other. Okay, I'm going to call this positive, which means this is positive, which means this is positive, positive, positive. So the direction of positive is this. Okay, you end up some weird stuff like this guy is positive down and this guy's positive up. That's okay. This is the same direction because it's a system and they're moving together. So because I have 3 A's and 2 alphas, I can write 5 equations, all right? So I have 3 equations that I can write. 3F equals ma, 1 for each one of these blocks, and 2 torque equals I alpha, 1 for each of the disks, okay? One last point that I want to make here is that all of these A's are the same. A1 equals A2 equals A3, and all of the alphas are the same, so we're just going to call this A. And all the alphas are the same. Alpha 1 equals alpha 2, so I can just refer to alpha. And lastly, not only are all the A's the same, all the alphas the same, they're also connected. A equals R alpha. So all the accelerations are connected somehow. Okay? Now, what I want to do quickly is, for part B, is sketch a diagram showing forces acting on these things. So here I have, let's start with this guy over here. Let's call this 1, 2, 3, 1, 2. Okay, so the guy at the bottom here, you have M1 is being pulled down by M1G. And then there's a tension here, T1. Okay, if you are this pulley right here, I'm going to just draw it over here. You have a tension, the same tension here pulling you down, T1. And then you have this tension here pulling you the other way, T2. Okay? Those are the only 2 forces that matter. If you are the block over here, let's call this guy M2. Then you have T2 pulling you to the left and T3 pulling you to the right. If you're the disk, you're being pulled to the left by T3. And then you're being pulled down by T4, and then if you're the block, you're being pulled up by T4, and then being pulled down by M3G. This is M3. Obviously, there is normal and m2g here, but these guys don't really matter because they just cancel each other. They don't really affect motion, okay? So here's all this stuff. Now, these are all the different forces. If you want to, we're going to quickly put some signs here. So remember, the direction of acceleration is this, okay? So when I write F equals ma for this guy, this is positive and this is negative, okay? This is positive and this is negative because it follows this direction. This is positive and this is negative, okay? Now, that being said, when you look at the torques, look at these guys here, these discs. The discs will have torques acting on them. So there is a torque pulling this disc this way. T1 right here, if you got a disc, T1 is pulling the disc like this down, right? So this is the torque due to T1, and this is the torque due to T2. We have to be consistent with signs. Spinning this way is negative in this problem because everything's going that way. So this is positive and negative. And we're almost done. Got to squeeze this stuff in here. I got the torque of T4. You can barely see that there. And then I have the torque of T3. The T4 one is positive and T3 is negative. Okay, hopefully you don't actually get a question like this, but you might get a much simpler version. I'm just trying to show you all the, for a particular case like this, what matters is the direction of the signs and all that stuff. Okay, so next one is much simpler. It's a simple yo-yo. So the idea is that you have a cylinder here that you let loose and it spins, so it accelerates down this way. Now imagine if you're holding if the string is here and the yo-yo's here and then it starts falling, it's going to roll like this, okay? So it's going to roll like this. Now, that's because the string is on that side. If you had a yo-yo here, then you let it go. It's going to accelerate like this, and it's going to accelerate like this. In this case, there are two different situations here. In this case, this is positive and this is positive. In this case, this is positive, this is positive. Notice that in both cases, A down is positive, but here the acceleration is positive this way. Here the acceleration is positive this way. All right? So it depends on the situation you have, but the key thing is that these two guys match each other. Okay? They got to match. So the accelerations have to both be positive together. All right, so how many equations do we have here? Well, how many types of motion? I have one object with two motions. One object with two motions. I have the same object has an A and an alpha. So that means that I'm going to write F equals ma once for that object, and I'm going to write sum of all torques equals I alpha once. Okay, those are the number of equations. Now let's look at all the forces. You only have one object. You have a force of tension that's pulling you up. Acceleration is down. Alpha is this way. Okay, so this is positive, this is positive. Notice that tension is going up, so tension is negative. And tension causes a torque. Tension causes a torque in this direction. Let me draw this a little bit differently. Where do I put this? Trying to move this away from here. Let's do this. Let's do tension over here. It's negative, and it causes a torque of tension this way. Okay. Now, does the torque of tension spin in the same direction as the alpha? It does. Alpha spins like this, right? And the torque of tension spins that way as well. So this is positive. Okay. So getting the sign here is very important. If you screw up the sign, you get the wrong answer. Okay. Something interesting that happens here is your tension is negative, but the torque of tension is positive. That's okay, right? So it's supposed to be like that. Don't freak out. Just because tension is negative doesn't mean that the torque of tension is positive. They're going to be different. So that's set up for this one. And let's do this last one here. I have a cylinder rolling downhill. It's a similar situation as the simple yo-yo in that I have one object with two motions. Okay, so I have one object that has both an A and an alpha. That's because it's rolling and moving at the same time, right? Therefore, I can write sum of all forces equals ma once, and I can write sum of all torques equals I alpha once. So before you can start solving these questions, you have to know which equations, how many equations you have to draw, you have to write, okay? Now here, we have this object here, and I'll tell you, we'll talk about this more later, but I'll tell you that the forces you have are mgx. Obviously, you have an mgy as well, but mgy just cancels with normal. These two guys cancel, so they don't really do anything. And there's a friction that goes this way. And the friction is responsible for the only torque you have. So there is a torque of friction. Now in this case, you are going this way, V, and actually draw it like this. You have a V this way, and you have an acceleration this way. Okay, you're falling this way and you're getting faster this way. So your omega is this way, and your alpha is this way as well. Okay, so down and spinning this way is positive. So this guy's positive, this guy's negative. This torque here is in the same direction as alpha, right? All of these guys are positive, so this torque is positive as well. Notice that just like what we had here, tension was negative, but the torque of tension was positive. Here, friction is negative, but the torque due to friction is positive. Okay, we'll check out these two examples later, but for now, I just want to introduce this. Cool. So again, just a big introduction. We're gonna do more of these. Hopefully this makes sense. Let me know if you have any questions, and let's keep going.